Okay, so we are still looking at our schematic design, and we're pretty much complete at this point. If you recall, we have been we did an ERC, a DRC, a design rule check. In particular, we set up our DRC matrix, and we found out that there were no errors. And everything's connected, and there's really nothing simple that's out of the ordinary, and that was reported by the session log where we ran the DRC, and it told us that after after it did the designs rules check, that there were no errors in our design, no elementary basic errors as far as the schematic is concerned. Okay, so now we're almost ready to begin phase two, but we have to complete the most important portion of our schematic design, and that is assigning footprints to each of the parts of our schematic. Um, in a schematic design that is meant to be end up on a PCB layout stage, we need to make sure that every single part in our design has a footprint assigned. This is mandatory. There is no way for you to successfully begin the PCB layout stage until you have assigned a footprint to all your parts. So all of our connectors need footprints, and all of our gates or the packages that these gates are part of require footprints. Just go ahead and move that in there. Um, control save the project. So how do we assign footprints, and how do we pick footprints? This is now where the difficulty in using OrCAD begins, okay? Because there has to be a little bit of a guess and check, and finding this information is not exactly obvious. So here's what we're going to do. We're going to, for example, let's say we pick all the connectors first. All right. And then again, I do Control E to bring the property editor, and then I'm going to look for PCB footprint, which is right there. So I have 4 devices and have ignore the yellow rows. We have 4 devices, 4 connectors, and we need to assign a PCB footprint. So what we need to add here, what we need to write in here, is a footprint name. Of course, we need to know what that footprint name is. All right, and many professional EDA software tools, they provide a rich library of pre-made footprints of commonly used devices that you can already provide onto that you can provide here, that you can enter here as a designated footprint. Okay, of course you need to know what a footprint looks like, so let me just not make any assumptions, and let's just go on to, let me just open a browser window. I'm going to show you some stuff. Let's just look at PCB footprint so that we are clear on what I'm talking about. Okay, images. All right, and well, here there's a variety of examples, but let's go ahead and pick, this looks like a good image right here. View image. So these are footprints. All right, that means every physical device for which you have a symbol for a drawing, okay, has a physical mapping. All right, I keep using the word manifestation, but what I really mean is mapping. A mapping from a symbol to a physical form that as it will appear on the PCB board. Okay, so these are, for example, a footprint for a ball grid array BGA type package. This could be a footprint here for a LQFP type of a package, low profile. All right, surface mount. Here are the footprints for a variety of DIP packages, dual inline pin packages, which is what we'll be using for this tutorial. Okay, these have through holes, plated through holes that again you have to drill, and it goes from one side and it comes out on the other. But all of these, for example, these have pads that only exist on the surface on one side and not on both sides. Okay, let's look at some more examples of footprints, see what I mean. Here's an up close of one particular footprint. Let me do a view image. Okay, from a different type of program, but just focus here in this area. Again, this is a looks like a let's see, 39 pin part. Okay, and again, this is this could be for a chip package. This could be a microcontroller, microprocessor. You know, and this is what a footprint looks like. You would have some kind of symbol in your schematic, but then this is what it looks like on the board. So eventually this translates to manifestation on the PCB board itself. Okay, let's take a look at this. Let's look at some diagrams here. If I can find an actual PCB that I can show you. Cancel. Oh, it won't let me go any closer, but you can see again now that this is an actual physical board, and as you can see, the physical board is composed of nothing but footprints. So in the end, the construction of a physical board in your EDA software toolset is basically of producing a board which with a bunch of footprints aligned accordingly to design criteria, right? So you have a combination of through-hole footprints, right? That you actually have holes that go through the entire board, and then you have some of the footprints which are for surface mount parts which sit on top of the board. And there are a variety of those parts in various types and forms that you can place on your board. So in the end, a schematic is a pictorial representation of symbols, and then the PCB board is a arrangement of the footprints which represent the physical mapping from the drawing to a physical manifestation. Okay, so that's what footprint is. So going back to the question, how do you know what kind of footprint you should write in here? What can you write in here? Well, before I answer that question, I want to show you one more thing. You need to first decide. So we have a drawing here. Let's say I have connectors or headers, or it doesn't matter what they are. These are interfaces between the board and something outside. These could be a connector to another connector wires. It could be just soldered wires. It could be a variety of things. This is just a symbol, but the part that represents the symbol, that's really up to you based on preliminary research that you do on parts that you want to use. Okay, what kind of parts are available for use? If you want to use a connector, well, what kind of connector do you want to use, right? There's a variety. Here's a search where I did for shrouded header. Okay, there's a bunch of connectors. What kind of connector do you have to use, or do you want to use? You know, what parts do you use depends on a variety of criteria, such as environmental conditions, temperature conditions. Is the part going to go into an oven where you do soldering reflow for your parts, and it needs to withstand high temperatures? Is the part going to operate, or the board going to be in high temperature conditions, low temperature conditions? What are the electrical characteristics and constraints of the part? How much current, how much power does the part have to be able to withstand? You know, all of these decisions come into play in you deciding. Of course, when you're starting out, you want to start out with the most common tools or most common components, and my recommendation to you is to look at, you know, hobbyist type of vendors such as SparkFun or Adafruit, which provide some very common parts, and start with common off-the-shelf parts. But regardless of the part that you use, you need to be aware of the footprint, which comes from the mechanical drawing, right? Let's take a view at this particular header here. Okay, so you have this particular header with this many pins in here, and this is what the part looks like, right, when you mount it on the board. But the board requires through-hole pins so that the metal pins can be fixed onto the board itself. That means you gotta drill holes. So this area here shows you, they call it the PCB layout. This is the footprint for this particular device, right? And it says that you have to drill holes with a diameter of about 1.02 millimeters and a spacing of 2.54 millimeters among them, and a row spacing also of 2.54 millimeters, right? So you always have to look at the mechanical drawing. You need to decide on a part, and then you need to look at its mechanical drawing. And if you're lucky, the software tool already provides a footprint for that part, but more often than not, you will have to figure out how to do this on your own. And the footprint part is the authoring of your own custom footprints. I'm going to look at that later in a separate video, but for now I'm just going to show you some of the information you have to be aware of. And this is where the challenging part begins. Drawing a schematic is easy. Now This is where you have to do a little bit of work. Here's an example of for example, let's say your version of a connector is a 9-pin connector. You need a 9-pin connector. Well, this is what the connector looks like, and this is the side view, and when you mount it to the board, these parts right here and the pins are going to go through the board itself. So that means we need to have a footprint that's going to designate what type of holes and what's the diameter of the holes needs to be. So once again, we have a diameter here around 3.2 millimeters. Okay, and just a quick note, many mechanical drawings use dimensions of either inches or mils and millimeters. Okay, so you need to be aware of the units. I can just tell by inspection, because I'm familiar with data sheets, that this is in millimeters. And then the diameter for the individual pins, for these pins right here, the electrical pins, it's 1.09 millimeters. And the spacing between holes in one row is 2.77 millimeters. And the spacing in between holes alternating between rows is 1.385 millimeters. So this is information you will need to make your footprints when you're making your own, or if there is a footprint that already matches closely, you need to verify that it follows the dimensions. You cannot just pick a footprint because it looks like it might be the one. You need to make some measurements and verify that the footprint fits the physical characteristics of the part. Battery connectors. How are you going to connect the battery? So for example, we have here a 2-pin, right? I'm saying that I'm going to connect the supply to a 2-pin connector. What is the 2-pin connector? That's up to you, right? You need to do some research. So I looked at a battery connector. So is it going to be these type of cables, and connectors? You need to look at mechanical drawings. Here's another one right here from SparkFun, right? 2 pins and a connector for connecting a wire. You decide what you want to do. Of course, you just need to make sure that it has 2 pins. But then there will be the physical manifestation. What does the mechanical drawing looks like? And therefore, what kind of footprint are you going to need to be able to mount this part onto the PCB? That is what footprints are when I'm talking about footprints. Let's talk about logic parts. So for example, let's go back to our schematic, back up, let's descend into one of these. So we have 3 unique types of logic devices, okay? And these are all 14-pin dips, okay? I want to use 14-pin dips, but if you did not use 14-pin dips, I use generic parts, okay? 7400, 7400, 7402. But the truth is that I did this for the purpose of this tutorial, but when you're doing a research, the part number is not going to be this simple, because the manufacturers have a variety of logic families and different part categories that they provide. Case in point, let's take a look at, for example, the data sheet I'm looking at here for the 7400. And there are a variety of families: 7400, 74LS, 7400, and 74S00. These have different characteristics, such as, what is the propagation delay, what is the current drive, what is the current sink, what is the power dissipation of the device, and they vary. So you need to look at the specifications side by side and make a decision. A good guide, for example, made by TI, is the Logic Guide, which talks about the rich variety of device families. So you can have a 7400 of LBT, 7400 of Fast Logic, 7400 of TTL, 7400 of high-speed CMOS logic type of device. Logically, they all do the same thing, but physically, they have very unique characteristics that make each family different from the other. And this is where you have to do some research and investigation to find out. There's also the logic levels in which the device operate for different device families. So, and they do a good job of just kind of summarizing what makes each family unique and what it is used for. Okay, again, I omitted all of that, but you need to be aware that in actuality you have the part numbers are far more complex. Let's go back to my sheet for 7400. The same part is available in a variety of packages, right? So I have my 14-pin dip. Okay, I have an 8-pin dip for different type of device. I have an LCC package type of device. It's completely different. They all do the same thing, but the different package types, right? They all have NAND gates. Okay, but the part that I wanted to show you again is, let's go down to the two things. Device number. Okay, so I said 7400, right? But here are the actual true part names. So you could have SN7400DG4, SN7400N, SN74LS00DG54, and of course, you know, there are different package types like SOIC. For this one, it's a pin dip, etc., etc. So you have a lot of research to do, a lot of decisions to make before you can actually just come down to a schematic and say, so this would be, for example, let's say for a pin dip, and I'm just drawing this as an example. Instead of my schematic saying 7400, which is not very indicative, you need to be specific. Now this is an obsolete part, so I will probably pick this one, SN7400N. So your schematic here should say SN7400N, and you need to be very specific for the part number. Okay. All right. Let's move on to the next. So footprints. We're talking about footprints. So to know what kind of footprint you need to look at the mechanical drawing of the device. There is simply no way around this. Okay. So if I want to use the 14 pin dip device, you need to do the most two important things is the separation between the rows of pins. Okay. So for A, that number is here 300 mils. Okay, 300 thousandths of an inch. And then the separation between the two pins, okay, it says here is 100 mils. And then the hole size for each pin here is between 26 mils and 14 mils. So it should be 26 mils, preferably a little bit longer or bigger than that, for the hole to be big enough for this to slip through the hole. Okay, so remember that spacing for this part is 300 mils, and the spacing between the pins is 100 mils. So if we find a footprint that matches this characteristic, we need to verify that it's able to hold this package physical characteristics. So let's go back to OrCAD, and we were talking about, let's start with the connectors. No, let's start with the let's go in there and let's start with the 7400s, 7402, 74. So let's start with the packages. Okay, how? Oops. Control Z, select, holding Control Shift, Control E. Again, PCB footprint. I need to specify a footprint for these parts. So what do I write in here? Okay, first question is we need to know is what type of footprints, what kind of names we have available. To do this, you need to navigate onto your installation of OrCAD. So on my computer, I installed it on a special folder called Special, OrCAD, OrCAD Lite, Share, PCB, PCB-Live, symbols. And the files you want to look at are the DRA and PSM. Ignore the paths for the time being. The DRA and PSM are the same. One is compressed and one is not, and they are both generated by the software tools when you're generating these footprints. But that's going to be a subject of a different video. But what I want you to notice is the names. Whatever names you have here, excluding the extension name, whichever names that you have in this directory, these are the names that you can put in here. So let's, for example, I said that I need a dip part. So there's a variety of dip parts, footprints that you can use. And obviously our part is a 14 pin dip, so there's only one part, a dip 14_3, right? So that's what I would write in here under PCB footprint, dip 14_3. Okay, but I wanna this only tells me the name. I need to verify visually what does the footprint look like. Okay, let's take for example that you were in a different situation. Hypothetically, suppose that the part that we need is a 20 pin dip, right? Will you write down dip 20? Will you write down dip 20_3? Will you write down dip 20_4? Will you write down dip 20_6? Which of these parts do I pick? They're all There are 20 pins. So I need to look at it. And unfortunately, to do this, I have to prematurely open the PCB editor um, in order for me to be able to look at the footprints. All right. So here's an example of an empty. The problem also is when we get to this, and we'll discuss this at length on the next video, is that once you jump into the PCB editor, you need to figure out how to even use the PCB editor in the PCB editor way. Okay, the OrCAD PCB designer, and it's just not necessarily very intuitive. You have to be very careful how to use it, so you get frustrated right away. But to see the footprints, you need to start a new project, and I started mine on just a temporary folder when you create new. And in fact, let me just show you that from scratch. So I'm going to just close this. I'm going to kind of redo this again from the beginning. I'm going to save the changes, and I'm going to start my OrCAD Lite. It's a demo version. It'll say that it is a demo version. Click yes. You could hit F10, and it'll show you the previous one. That's why it reopened my. So let's just pretend it didn't. So I'm going to say new. I know you can't see it, but I'm just going to say new. No. And then you'll have to find a location to do this. So I created a temporary, in my OrCAD tutorial project folder, I created a folder called temp, just for the time being. Click on it, open it, and then just give the board around. I call it temp. Open, click OK, and it'll start a new project. Press F10 to view the grid, or you could hit the grid icon here. You can use the mouse scroll bar to zoom in, all right, and scroll down to zoom out. You can push the scroll bar down and hold it like a button to kind of pan around on the image. Okay, but let's just see how to view. I just want to inspect the footprints. So to do so, we go to Place Manual here on the corner, and then the placement panel will come up. Okay, I want to see the package symbols, and there's nothing under package, so I need to go to Advanced Settings, Library, go back to Placement List, and I can expand the list. And now all of these, everything that was in the symbols directory, okay, is now presented here. And now we just see the names. And you're just gonna have to go to see for capacitors. I imagine that the cap is what that means. And then there's some standard devices for surface mount devices, and you're just gonna have to go through these. And this is the part that's kind of you need to be familiar with standard packages. Okay, what the traditional packages look like. But our interest is in DIP20. Our part is actually 14 pin. But I just wanted to show you, let's say we needed the DIP20, I just wanted to make my point here. If you check it, then it'll be under the mouse, and then you can click and place it. Okay, and then go back in here, DIP3, I check it, and then I click, I place it. Then let's jump to DIP26, check it, I place it. Okay, are these, obviously it depends on the 20 pin package, but let's go ahead and click OK and dismiss this window for now. And let's turn off the grid. F10. Okay, I want to find out whether this device has the right spacing, has the right hole size, and it has the right pitch between the two pins. To do so, you can use the measure tool. Once you click it, the measure tool is engaged. You know this because on the bottom left hand corner it says show measure, and it will be so until you right click and click done or hit F6. Alright, this could be very confusing for people and problematic because you expect to press escape, which I just did to dismiss the menu, but escape is not going to exit the. If I hit the escape key, it doesn't do anything, it tries to measure. Right, and this is a taste of how things are very different in OrCAD Capture. But anyways, my measure tool is active. I want to measure the spacing between the two rows. So let's click here once, and let's click here second, and then a measure window comes up, and it says that the distance is 300 mils. right? And then I want to measure the distance between this pin and this pin here, adjacent pins, and the distance is 100 mils. Now for our 14-pin dip package, I said that that's what we needed, right? What about this one? The spacing between this and this is 300 mils. This and this is 100 mils. So these are the same package, but we need to also look at the holes. Obviously, just by looking at this, the spacing of this is 600 mils. So you need to verify that the package that you're going to use for your part has a spacing of 300 mils if it were a 20-pin device. And the spacing between these two pins is 100 mils. So the spacing between these three varieties of dip 20 footprints is the same, but the spacing between the sides is not unique. Well, it is between these two. Okay. Let's say I want to delete this parts from my window, so I have to first exit, right click, done, the measure mode. Notice that it says idle here on the corner. Alright, and I want to delete it, so Control D, and I'm going to select everything, and then I'm just going to click anywhere on the side and it'll go away. My delete mode is still active, so right click F6 to exit delete mode. Alright, let's go back to place manual, and I want to look at my 14-pin dip because that's what I want to use for my actual package. Again, I'm just looking at investigating. Okay, so this is what the package looks like. Let's dismiss. Let's click OK, and I'm holding down the middle mouse button and just panning. Then I can scroll in to push it in a little more. I'm going to engage the measure tool, and I'm going to measure. So from this pin to this pin, 300 mils, and from this pin to this pin is 100 mils. Now I can see, let's go back to my sheet, that was precisely 100 mils spacing, and 300 mils is shown here, the spacing between the pins by the A. You got the table here, 300 mils. Okay, so it looks like this could be the part to do so. We dismiss this, we turn off, we exit measure mode, so right click, done. Alright, I can right click the pin or the pad. Let's pick a different pad here. Right click on the pad and then say show element, and that'll give me some information about the hole itself. And it says that it has a diameter drill of 36 mils. So that's the hole. If I go back to my schematic again, the widest part of the pin needs to be maximum 26 mils. So a diameter of 36 mils will be sufficient for that pin to go through the hole. Therefore, my conclusion is that dip 14, whatever it was called, let's go back to my symbols here, dip 14_3 will be the, and I'm going to minimize this and get back to, so I'm going to say dip 14_3 tab. Again, click here, dip 14_3 tab, click dip 14_3 tab. Okay, these are all the occurrences, by the way, but we only do on the primary sheet. So all my logic symbols, control, let's hit apply, control S to save that. What's going on here? Let's just close this panel. Let's go back here to the complete design, click it, control S, save everything. Let's go back. So we have footprints for our logic devices, for our parts. Now we need footprints for the connectors. And again, that depends on what type of connectors you use. But again, let's just take a look at what we have at our disposal. Is there anything that looks like header or connector? So let's see. We can use jumper. Probably jumper will do. What does jumper look like? So we need a 2-pin jumper and we need a 4-pin jumper. So let's see what a jumper looks like. Oh, sorry. Let's go back to OrCAD and let's bring up the placement manual. What's going on here? There we go. Let's take a look at jumper. Alright, so I'm going to need a 2-pin jumper. I click on it, and that's what it looks like. And I'm gonna need 4-pin jumpers. I click on it, that's what it looks like. Let's see what else we have here. Do we have headers? Nope, no headers. That's it. Okay, let's zoom in on these, pan a little bit. So now the headers. Let's take a look at the headers. So let's go back to some of the drawings I was looking at. So let's say I use a standard header from a company that produces headers like these, and they produce both 2-pin varieties and 4-pin varieties in a single row. I'm just looking at this as an example. I'm going to make an assumption for demonstration purposes. For the record, 2.54 millimeters is actually 100 mils. So therefore, the spacing is 100 mils in every direction. So let's go back and pretending that this is the part where, again, that is only 4 pins wide and 2-pin variations only. What are the dimensions of these? Can these footprints called jumper be sufficient for my needs? Well, let's just see. Again, in the end, it's all about drilling holes or putting pads. And the fact that the footprint is called jumper or something else is not really as important. Of course, the name is supposed to be indicative of the part that is going to be matched with on the symbol, but you just want to find a footprint that will meet your demands. So once again, activate the measure tool, and the distance from here to here is 100 mils for this part, and the distance from here to here is 100 mils for this part. So these jumpers will be ideal for header type. Let me show you what a header looks like. Let's see, do I have a header? Oh, while I have this up, if you want to know about all the parts that are available and mechanical types and components and types of headers that you can use in the rich library of components that you have at your disposal, I highly recommend that you sign up for one of these puppies. Okay, a free catalog from Mouse and Electronic, and this will be your Bible. Just go through it all the time. Even if it goes out of date, it will be a great resource for you to learn about what components, what connectors, what are they called, what's the correct terminology that is used for describing parts. You need to have that. Anyways, headers. Let's just look at PCB headers. Is it called headers? Something like this. Okay, this is a good example. Right. A lot of amateur designs and for simple designs, they have things like this that you can just use and you can connect wires to. And this, you get the male version. You can also do the female version connector, for example. Let's see if I can find some more images that illustrate. For example, like this. Right, you could have this. This could be a header. This could be a jumper. Right, the spacing between this will be approximately 100 mils. You need to verify, and then the drill diameter will be sufficient for you to fit the hole in it. If we go back to that image, the whole, I'll have to convert 0.64 millimeters to mils. Let's see, 0.64. It's 25.19 mils, so around 25 mils. The hole diameter is 36 mils, so therefore we're still good. Okay, let's go back. So therefore, I conclude that jumper 2 and jumper 4, these were the names for these particular footprints, will be sufficient for my design here, for my jumpers. So I'm going to select my jumpers. I'm holding the control key, click, 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 then control E, and find the PCB footprint entry. And okay, the names, I can't see what the names are. So the top is input, output, and the third one is supply. Okay, the third one is the jumper 2. And then all the other ones are going to be jumper 4. Jumper 4. Jumper 4. Apply. Okay, close it, right click, close. Let's get back to our design. Select the design, control save. Okay, so I think we're done. The design is done. It's labeled, it's beautified. It's clean. It's got title blocks. It's got additional descriptive text. For clarity, buses have net labels. Individual wires of interest have nets. In fact, I'm going to go ahead and when you hover the mouse over a wire, it will tell you what the net name is. Sometimes for critical key wires, you may want to relabel it so that you can find it on the PCB board when you're doing it instead of having some random name such as N00245. I'm going to push N for net alias, and I'm just going to type CLK for clock, hit enter, and make sure you click on the wire. And now escape. And now if I hover over the wire, the name is clock. Same here, I want to make sure I can really find BCC and ground. And these are automatically labeled because the global nets sometimes they label the wire that they are attached to. Okay, Control S again. And I think I'm done. So I have all of my parts. I have all the parts have reference designators. All of the reference designators are unique among my occurrences. I did the DRC check, it passed, and I did a footprint for all the parts, and it's good. So we are ready to generate the netlist, which is the final step. The netlist is, as the name implies, it is a list of nets that specify the connectivity of your entire design. In other words, what is connected to what. That's what a netlist is. So how do we generate a netlist? We go back to Project Work Manager, select the design, and then click on this icon, create netlist. Okay, we go ahead and create the click on the icon. The create netlist panel shows up. Okay, leave everything by default. Okay, let's go ahead and click on that, create or update PCB editor. Now, when you're creating a brand new PCB board, and that is what we're doing right now, the first entry should be empty. The second entry is where the name of the board will be placed. By default, it will be placed into a folder called Allegro, and then the name of your project will be used as the name of the board. So the .brd file will be your netlist board, and it will be the PCB board itself. In addition, board launching options by default, after the create netlist is done, once that is successful, it will automatically open the board file in the PCB editor, which is fine if you have a paid license. If you have a demo version, I recommend that you do not open the board file and do that separately, because it is a demo, it will fail. Okay, now suppose you make a change to your schematic and you need to change the board. Let's say you are already in phase 2, you're working on your PCB layout and you decided to make a change. You need to go back to the schematic. Well, you go back to the schematic, but then you need to specify as an import board file the same board file. If you leave this empty and you make a change to your schematic that you want to reflect onto your board later on, it won't happen. So again, just FYI, keep that in mind. But for the time being, we're creating the netlist for the first time, therefore the input board file has to be empty. Alright, and this is all we need. We don't need to look at anything else. Let's just hit OK, and if it'll say the Allegro folder does not exist, so it'll create it automatically. Just say yes, and then it's doing its thing. And if we have no issues, and how do we find out? We need to look at window session log. Okay, and it's creating the netlist, the board file. Let's see, it looks like it starts from, so here's when we did the DRC, and here's when we did the netlist generation. And you look, if there's an error, first of all, it will fail. And you can look at this, to see if there's anything that grabs your attention, but it doesn't look that there's any errors. So therefore, the netlist is good. Let's take a look at our folder. Oh, let's save it. Control S. So we're done, ladies and gentlemen. Now we're ready to start phase 2. Now let's take a look at our project folder. Okay, so I'm looking at OrCAD tutorial. That's where the folder I created. I double click on it, and we have our design file, which is part of our specific design, and then there's the OrCAD project file. So your design file is actually contained inside of a OrCAD project file. So everything goes together. And then Allegro is the folder that was created specifically for the PCB. So if we go in here, double click on it, here's the information, but our key file is this file right there. And that is the board file that we're going to use to begin phase 2, which is the now the layout phase of our existing schematic design here. And to do that, we're going to cover that into a second video. So that concludes this video, this first part of the video. I hope that it was helpful for you, and that's it. Look for the second video, second part, and get started. Like I said, PCB, the OrCAD part, the capture, the schematic portion, the software, I think is very intuitive. It's very well thought out. Everything works the way you expect it. You use the mouse to move, you use the left mouse button to click and select, and you can just select everything and click and drag things out of place. If you want to lay a wire, you press the W. If you want to place a part, you press the P. If you want to place a no connect with an X, you just hit the X key. Everything is very intuitive. Okay. When we go, except for the footprint part, it requires investigation. It requires you to have a lot of information ahead of time, a lot of knowledge. Okay. You need to do research, parts, part numbers, footprints. Does it exist? What do I have? You have to work within the constraints of the demonstration version. That's the other the thing. I want to make it clear that the full version license has a very rich library. But in either case, and in my personal experience, I almost always find myself having to make my own footprints, because you just cannot make footprints for every possible part. It's just not realistic. So it's a skill you have to know. You have to know how to make footprints. So we're going to look at that in a separate video. We're trying to restrict ourselves here into trying to just make use of the demo and trying to make use of the resources that are available by way of the demo software. Okay. Another thing I wanted to make clear is that, again, there's no special, even though there's nothing special about a footprint. It is just basically, it says where are the holes going to be, what are the hole sizes, what are there's certain information such as the solder mask and things like that. We're going to discuss that later. Okay, but it's not, even though this was called jumper, I can use the jumper footprint to connect any device that has a spacing of 100 mils. A hole diameter is at least that fits this, and the same thing. So this I can use this pattern to just solder wires into it. I can stick wires into these holes if this is small enough. I could use a header, a 2-pin header, a male type 2-pin header. I can use the same footprint to hook up a 2-pin female header. I can use the same footprint to hook up, a shrouded header. I could maybe even use the same footprint to connect a capacitor in it. If you bend the pins a little bit and stick them through there. So there's really nothing special about the footprint name, other than you need to make sure that mechanically the footprint can meet the requirements of the parts that you're using from a physical dimension standpoint. For mass production, this is actually very important. You need to be very meticulous. For personal work, for hobbyist work, you can normally, if you miss a little bit, you can kind of bend the pins and kind of get the part in there. Of course, you gotta be perfect when you're doing this professionally. But there's really nothing special about the naming. So I'm saying that because I want you to research. I want you to get in here and just to lay parts, see what they look like. Another good strategy is you can print. Many people, and I do this myself, print what you have here onto a sheet of paper and make sure that the scaling of the print is 1:1. That means that the exact dimensions here will be, the scaling of the printout will be exactly as it will be if you actually had the board fabricated. So that means you can look at these footprints on a sheet of paper, and if you happen to have the parts in question already, let's say you purchased the parts already, you can just go ahead and place the parts on your sheet of paper and see if the pins line up, right? And you will be able to tell right away whether you are way off or whether you need to rethink your strategy. Okay, the footprint thing, the footprint question must be known, must be decided, must be finalized. You just cannot go through a complete design and then find out that your footprints are wrong. this is a complete disaster. You need to know what footprints you're going to use, and you need to be sure, 100% certain, it will do the job for your particular needs before you do anything further. I haven't done anything. I haven't started layout. I haven't done nothing. All I'm doing is evaluating the suitability of these footprints for my parts. That is a very important message, and it's the most important part before you finish the schematic design in OrCAD and move on to create the netlist and move on to the PCB layout. Okay, so that's it. Let's go ahead and stop here. Thank you for your patience and your time, and go take a look at the second video. Phase 2, PCB layout in OrCAD. Thank you.